Hello and welcome. In this video, we're going to take a deep dive into one of the fundamental concepts in AC circuits, the RL parallel circuit. We'll start by looking at the circuit diagram, then we'll walk through the mathematics that governs its behavior, and finally, we'll bring it all together by drawing and understanding its Phasor diagram. By the end, you'll have a clear picture of how voltage and current interact in this type of circuit. Let's begin by looking at the image provided. On the top left, we see a diagram labeled Fig. RL parallel circuit. Let's break down what we're seeing. On the far left, there's a circle with a sine wave inside it. This is the symbol for an AC, or alternating current, voltage source. This source provides the electrical pressure that drives the circuit. The voltage it provides is represented by the phasor V bar. The bar on top of the V tells us we are dealing with a phasor, which is a quantity that has both a magnitude and a direction, or phase angle. From this source, a wire extends to the right and then splits into two separate paths. This splitting is what makes it a parallel circuit. Think of it like a river splitting into two smaller streams. The top path goes through a component with a zigzag line, labeled R. This represents a resistor. A resistor's job is to resist the flow of current. The current flowing through this resistor is labeled IR bar, and the voltage across it is labeled VR. The bottom path goes through a component with a coiled line, labeled L. This represents an inductor. An inductor stores energy in a magnetic field when current flows through it. The current flowing through the inductor is labeled IL bar, and the voltage across it is labeled VL. After passing through the resistor and the inductor, the two paths join back together and return to the voltage source, completing the circuit. The total current that leaves and returns to the source is labeled I bar. Now, the most important rule for any parallel circuit is this: the voltage across each parallel branch is the same. The image notes this at the top: VL equals VR equals V. This means the voltage across the inductor is exactly the same as the voltage across the resistor, and both are equal to the source voltage, V. This is the key to understanding parallel circuits and will be our reference point for the entire analysis. Now, let's move to the right side of the image and look at the equations. This is how we mathematically describe what's happening. The first line says, by KCL. KCL stands for Kirchhoff's current law. This is a fundamental law in electronics that states that the total current entering a junction, or a split point, must equal the total current leaving that junction. In our circuit, the total current, I bar, from the source reaches the split. Some of it goes through the resistor as IR bar, and the rest goes through the inductor as IL bar. So, according to KCL, the total current I bar is the sum of the two branch currents. The equation is written as I bar equals IR bar plus IL bar. It's crucial to remember that these are phasor quantities. This isn't simple addition like 2 plus 3 equals 5. It's a vector addition, meaning we have to consider the phase angles, or directions, of the currents, which we will visualize later in the phasor diagram. Next, we see a version of Ohm's law for AC circuits: V bar equals I bar times Z. Here, Z represents the total impedance of the circuit. Impedance is the total opposition to current flow in an AC circuit, which includes both resistance and reactance from the inductor. The equation is rearranged to show that the total current, I bar, is equal to the total voltage, V bar, divided by the total impedance, Z. The next line substitutes this into our KCL equation. Instead of I bar, we write V bar divided by Z. So the equation becomes V bar divided by Z equals IR bar plus IL bar. Now, let's define the individual branch currents using Ohm's law. The current through the resistor, IR bar, is the voltage across it, V bar, divided by its resistance, R. The current through the inductor, IL bar, is the voltage across it, V bar, divided by its opposition, which is called inductive reactance. Inductive reactance is written as J times XL. XL is the magnitude of the reactance, and the J is a mathematical operator that represents a positive 90-degree phase shift. So, our equation now expands to V bar divided by Z equals V bar divided by R, plus V bar divided by J times XL. Notice that the voltage, V bar, is present in every term of this equation. Because it's a common factor, we can divide the entire equation by V bar, which simplifies it to 1 divided by Z equals 1 divided by R plus 1 divided by J times XL. This equation is fundamental. It shows how the reciprocals of the individual oppositions add up to give the reciprocal of the total opposition. This leads us to a new set of concepts that are very useful for parallel circuits. In electronics, sometimes it's easier to talk about how easily something allows current to flow, rather than how much it opposes it. This ease of flow is the reciprocal of opposition. The image introduces these terms. The reciprocal of impedance, 1 over Z, is called admittance, and it's represented by the letter Y. Its unit is the Siemens. Admittance is the measure of the total ease of current flow in the circuit. The reciprocal of resistance, 1 over R, is called conductance, represented by G. It measures how easily current flows through a resistor. The reciprocal of reactance, 1 over X, is called susceptance, represented by B. It measures how easily current flows through a reactive component like an inductor or capacitor. In our case, since we have an inductor, we have inductive susceptance, BL, which is equal to 1 divided by XL. The image also points out a key mathematical identity: 1 divided by J is equal to negative J. Now, let's rewrite our simplified equation using these new terms. 1 over Z becomes Y, admittance. 1 over R becomes G, conductance. And 1 over J times XL can be rewritten as 1 over J times 1 over XL. We know that 1 over J is negative J, and 1 over XL is BL. So, this term becomes negative J times BL. This gives us the final equation in the yellow box. Y equals G minus J times BL. This is the rectangular form of the total admittance. It tells us that the total ease of current flow, Y, has a real part, the conductance, G, and an imaginary part, the inductive susceptance, negative JBL. Now for the main event, the Phasor diagram, labeled Fig. Phasor diagram. This is a visual representation of everything we've just discussed. It shows the relationship between the voltage and the different currents in the circuit. The reference phasor. In a parallel circuit, the voltage is the same across all components. Because it's the common quantity, we use it as our reference. In the diagram, you see a horizontal arrow pointing to the right, labeled V, reference. This is our starting point. We will measure all other phase angles relative to this horizontal line. The resistor current, IR bar. Now, let's place the current through the resistor, IR bar. A key property of a pure resistor is that the current flowing through it is perfectly in phase with the voltage across it. In phase means they reach their maximum values and cross zero at the exact same time. To show this on the diagram, we draw the phasor for IR bar directly on top of the voltage phasor, also pointing to the right. The diagram labels this as IR, in phase. The inductor current, IL bar. Next, let's consider the inductor current, IL bar. A key property of a pure inductor is that the current lags the voltage by 90 degrees. Lags means the current waveform is delayed, it reaches its peak value a quarter of a cycle after the voltage does. On a phasor diagram, a 90-degree lag is represented by a rotation of 90 degrees in the clockwise direction. So, starting from the reference voltage, horizontal, we draw the phasor for IL bar pointing straight down. The diagram labels this as IL, lagging. The total current, I bar. Finally, we need to find the total current, I bar. Remember our KCL equation, I bar equals IR bar plus IL bar. This is a vector sum. To do this visually, we use the head-to-tail method. Imagine the phasor starting from a point labeled A. The resistor current, IR, goes from A to a point labeled C. The inductor current, IL, goes from A down to a point labeled B. To add them, we can take the inductor current vector, from A to B, and move it so that its tail starts at the head of the resistor current vector, at point C. This creates a new line from C down to a point labeled D. The diagram notes that the length of is equal to the length CD. The resultant, or total current phasor, I bar, is the vector drawn from the very beginning, point A, to the very end, point D. This is the diagonal line in the diagram. The phase angle, phi. Now, look at the final picture. We have the reference voltage V pointing horizontally to the right. We have the total current I bar pointing down and to the right. The angle between the voltage phasor and the total current phasor is called the phase angle, and it's labeled with the Greek letter phi. Because the total current phasor I is below the horizontal voltage phasor, we can see that the total current lags the total voltage. This is a characteristic feature of any circuit that is more inductive than capacitive. The angle phi will be somewhere between 0 and 90 degrees. So, let's quickly recap what this phasor diagram shows us. We start with voltage as the reference because it's common in a parallel circuit. The current through the resistor, IR, is in phase with the voltage. The current through the inductor, IL, lags the voltage by 90 degrees. The total current, I, is the vector sum of IR and IL. This resultant total current, I, lags the supply voltage, V, by a phase angle phi. This diagram perfectly visualizes the behavior of an RL parallel circuit, showing not just the magnitudes of the currents, but their crucial timing relationships with each other and with the source voltage. Thank you for watching. I hope this detailed breakdown has helped you understand the RL parallel circuit and its phasor diagram.